and this is my final project for CSCIE89 deep learning. I will show a case study in manufacturing for text recognition in motor plates for predictive maintenance. So what is predictive maintenance? There are many types of maintenance that can be done to a machine in many factories. Reactive maintenance is to fix the machine whenever it breaks. Preventive maintenance is maintaining it at regular intervals so it doesn't break. Predictive maintenance is predict exactly when it will break and fix it accordingly. And prescriptive maintenance is let the machine help you decide to avoid predicted failures. And for the company I work for, we focus mainly in predictive maintenance. So what is it for? It's good for smart replacement to know exactly when to replace something that's gonna break in the machine and to schedule correctly the maintenance. It can be used for Internet of Things, as we use a lot of sensors to get the data from the machine, decrease service loss, lower the risk, improve workforce, asset availability, and recover revenue. So how does online predictive maintenance work? The sensor is connected to the machine, and it sends data to a gateway that sends the data to the cloud. The data arrives in our office, and there we have a lot of analysts, specialists, and AI algorithms that will see whenever a machine will break and let the people that work in the factories know. So this is the data that we have. This is a vibration signal spectrum, and as you can see here, in the probably around 16 hertz is when the RPM that is the frequency that the machine runs in, and this is the data that we have to analyze and classify whether it will break or not. Here you can see it has like this dot, this red dot, which shows that probably something went wrong and might be not working perfectly, and it can break soon if we don't do anything. So the project is to generate a more accurate analysis. And so in order to do that, we need to know more about the motor, such as the RPM, rolling bearing manufacturer, frequency, and power. So why is the bearing important? The failure frequency formula is given as a function of the rotation, the nominal diameter of the rolling element, such as the rolling bearing, the contact angle of the bearing to the machine, and the number of rolling elements. And this formula is very important to us because we need to know the failure frequency that's happening right here, which frequency it will happen. And depending on the frequency, we can see exactly if it's a lubrication problem or if it's a bearing problem or if any, like many types of failures that we can tell just by looking at the frequency. After knowing the bearing, it's possible to find these 4 variables in the table. And so every bearing manufacturer has a table that shows exactly the nominal diameter, the contact angle, and the number of rolling elements in each machine. The RPM, it's important for the vibration analysis. It's used when calculating all the defect frequencies, the failure frequencies, defect failures frequencies, and failures frequencies is the same thing. And so the engine only vibrates if it's running. If the motor is paused, it's not running, so it doesn't vibrate. So the faults are all found whenever it's running, and we need to know whether it's running. So the RPM here, we can see whether the motor is running or not. The frequency, it's important mainly because we can find electrical fault, not vibration analysis, but the electrical fault. It's only mainly important because of the electrical fault. It can be one, not lubrication, but electrical. And this is important. It is not really as important as the bearing or the RPM, but it's still important. And it's not hard to find because you don't really need a motor plate to know, since like in the US, it's only possible for 60 hertz. Or Europe, I think it's 120 hertz, 120. And the power of the engine shows how important the machine is for the company. So a machine that's about 30 horses is no big deal to get it So it breaks and nothing big will happen. Not a lot of money will have to be spent to replace it. But say a machine of 600 horsepower breaks, then it would be very expensive to replace it. And this is my data. This is a nice plate from Toshiba International Corporation in Texas, and we can see some information here, like the model number, the voltage, RPM. Anyway, all this information is important because with this we can know exactly the failure frequency. This is another example of plate. As you can see, they don't follow a pattern. They are very different from each other. Or this, many are rusted and dirty and just not looking pretty. So what was my approach? So I used deep learning algorithms, and I tried to use the transformer, Keras OCR, and Google Vision. So my first algorithm that I tried to use was Keras OCR because it is free, and since I don't have the data, what's written here, sometimes even AI can read better than I can this data in question. It's a free library that we can use to read the text. So I used Keras OCR, and here is my code. First, I had to connect to MongoDB, and from Mongo, I had to get inside the database for my company, and this is where I get the data from the database. And here I collect all the pictures, and you can find it in the directory data, all the pictures. I downloaded it, and then here is all my functions to predict the result. Here I'm loading the pipeline with these models that come previously built inside Keras OCR. Here I'm loading all the images and printing the image with boxes. As you can see here, they got Keras OCR got advanced, got design, and then GN, and it's not very squared, you know. So here it's printing the words. As you can see, worldwide, advantage, dashed, maybe, I don't know where I found dashed, but it's here. And here are another results for this image, which is a little bit harder to get to see. And here we can see many numbers. So this is not good because all my results should be in numbers. So what I did was, if I find hertz or FLA is the rolling bearing number, RPMs, amp, or volts or HP, those are the things that interest me. And here I ran it into some images, but I couldn't find any. As you can see here, nothing much was found, only for this one, which was 60 hertz. And I got results, but not what I was expecting from it. And after that, here I show some of examples of the Keras. And another example, this was a successful case because I actually found 180 volts here and was accurate, so this was good. And here I found 60 hertz. Okay. And then I tried Google Vision. Google Vision was much easier to work with, much easier. This is my code for Google Vision. So you have to generate a key, a credential. I generated it and uploaded it. And here are my functions to predict it. What are some functions? And here I'm uploading all the data into the result API and saving all the results into this file, which you can find it here in the response. And I'm saving them all into pb.gz. And then later, I'm saving it to a CSV file. And you can see here that maybe my algorithm didn't work as good. I need to change something here, but that will be a next step. And here I'm plotting all the images with the words that it found. As you can see, even this image that is tilted 90 degrees, it found the words. So for volts, it found for 160, HP, it got the RPM, the everything. Here are the bearings numbers that I needed, the model for the motor, and this was a very successful example. And here is another example that I tried to. As you can see, this is the same one that I tried using with Keras OCR, and it got a very good result, impressive result actually. Okay, so Google Vision is made by Google, and my experience was great. Here is my result, and here is the Keras OCR, and here is the results for Google Vision. So I got the same plate to show exactly the difference between each of them. Which was my transformer. The transformer architecture, as we can see in the picture here, is composed of an encoder, which will encode the messages or the data in a way and then decode it in another way. And so the way it would work, it would be that I would encode my images and decode them as the OCR and the text that I wanted to show. And for the transformer, as Google released Attention is All You Need paper, it would have the multi-head attention, which would focus only on my keywords. So I would need to ingest my transformer with my keywords as for the attentions, and I would get the OCR, the text, all written perfectly. Unfortunately, my transformer didn't work because all the data I had was not translated yet. So I couldn't train my network in a way that I needed to get the results. And here is the code that I wrote for transformer. As you can see, here I'm importing all the libraries and getting the file path, putting the files into an NumPy array, doing the tokenizer to gather the data that's going to be the label for each picture. And here I'm doing the buffer size, creating some functions that I found on the tutorial for transformer. And here I'm creating more for the padding mask, for the attention, the multi-head attention I'm creating here. And here the decoder layer, since the transformer is composed of the decoder and the encoder. Here I'm creating my model, which I'm using the ResNet 50. Here is the actual transformer. And then here I call it and create a number of layers, and plotting the learning rate and the train step, and the accuracy, plotting the accuracy, creating masks. And then here's the train step created function, and here is my epoch where I will call it, and to evaluate my model here. And here for finally predicting an image, which I will put some image and expect to get the text recognition for that image. And here I'm plotting attention. So my challenges for this project was collecting the data, because the data stays in the company's database. So I needed to get a request to actually get that data from the company and actually have access to the company's database, which stays in Brazil. So I had to have the PuTTY installed in my computer and create a tunnel network. Also understanding the data, since it's very new for me, this vibration analysis and predictive maintenance, I needed to request a lot of information from our specialists to understand what I'm actually doing, why I'm gathering this data from all these motor plates, and what would it be used for. So what is the RPM, what is the frequency, and what's the need of it, to actually have something to present for this project. Formatting the data was another issue. It always is for me. I feel like the time that I most struggle with is when formatting the data and getting the NumPy arrays and other kinds of data to load it to the model and making it padding and the right format. So this is another challenge for me. The actual data was a challenge because, as you saw, a lot of the images were very poorly taken because they were all taken by humans. They can be blurry, they can be, even the plates can be rusted because the engines or the motors can stay anywhere. So especially like very hot places or places where they need to throw some acid on top of the engine, so the motor plate is very corrosive. And after that, of course, learning to work with different types of technologies and libraries, it's always a challenge to learn something and how to use it. And that was one of my challenges. What are the next steps that I plan on doing from here? Maybe write a better algorithm to select the value near the words of interest. So maybe actually write a CSV file perfectly with the values and what the keyword goes with it, which keyword goes with it. And then I was thinking maybe load my transformer model with that CSV file that I created from the Google Vision API. And that way I could train my transformer and actually get my code to work. So I thank you very much for paying attention to my presentation,